In residential design and construction, there are not many features that offer the same blend of lifestyle value and architectural appeal as elevated decks. Whether projecting off a second-story living room or wrapping around the upper level of a hillside home, these outdoor platforms transform the domestic experience by blurring the boundary between indoors and outdoors. Decks provide spaces for social connection in an atmosphere blended with panoramic views and fresh air. They are especially desirable in scenic or temperate climates, often serving as an extension of a family's living and entertainment space. But this elevated enjoyment comes with elevated risk. Unlike patios or ground-level terraces, elevated decks at the second or third story introduce the potential for falls from significant heights. This is a serious hazard. At the edge of these platforms lies the guardrail system, which is sometimes a deceptively simple barrier. Often taken for granted, this system is one of the most critical life safety features in residential construction. When properly designed, installed, and maintained, it can prevent fatal accidents. When neglected or improperly built, it can become the very source of catastrophe. There have been numerous reports documenting guardrail incidences resulting in life-altering injuries and tragic outcomes. These incidences occurred when the guardrail systems failed under the weight of people leaning on them or pushing against them. These failures, when investigated, often trace back to common patterns: weak anchorage, insufficient fastening, wood decay and corrosion, or a lack of proper structural design of the system. Many of these systems are constructed by well-meaning contractors or homeowners, sometimes without a full understanding of the structural demands involved. Guardrail systems, in particular, are frequently misclassified as aesthetic or finish carpentry, rather than as critical structural safety components. This misconception is dangerous. A guardrail is not merely a visual boundary or decorative edge. It is a structural system that must resist concentrated lateral and vertical forces acting at the top of the guard. Its failure can mean the difference between a secure outdoor gathering and a tragic incident. This video will focus on the anchorage of guard posts that are supported along the perimeter on the side face of deck framing. This is the first of several videos that we will cover in this series on decks and balconies. The next video on this series will look at guard posts that are supported at the top of deck framing. In both videos, we will look at the design considerations that are important to engineers when it comes to the anchorage of guard posts. We will use real design loads to analyze the forces that are developed at the base of the anchor so that we can gain an appreciation of the magnitude of minimum forces that typical guard post anchorage connections should be designed to resist. Typically, there are two types of anchorage solutions for cantilever guard posts. First, there are guards that are supported on the outer or inner face of deck perimeter framing. In this case, the guard post is framed against a rim joist or beam. One of the framing methods in this category of solutions involves anchoring the post to the deck using 2-through bolts. The top bolt is attached to an anchor device that is fastened to the deck joist or blocking, while the lower bolt is secured to the rim joist or beam. When the guard post is pushed outwards, the anchor prevents the post from pulling away in the direction of the force by securing the post to a deck joist running perpendicular to the deck edge. For cases where deck joists are running parallel to the direction of the railing, the anchor device is secured to wood blocking that is provided between the parallel joists. Once the force enters the deck joists or blocking, it is distributed throughout the deck through the decking, which is nailed to the deck joists and blocking. We will look at an example of this type of anchorage shortly. The second type or category of anchorage solutions includes guards that are supported on top of the deck framing. This is typically used with a steel guard rail system and includes a post with a base plate. Typically, the base plate is pre-drilled with holes which are used to anchor the base plate to the wood framing using lag screws that penetrate through the beams, joists, and blocking elements that are carefully designed to support the forces from the base plate and lag screws. When the guard post is pushed outwards, the lag screws prevent the base from rotating outwards and transfers the force to the deck framing below. The force is then distributed to the other deck framing members. As we have just mentioned, this type of anchorage will be the subject of the next video in this series. This is part of an exterior deck at the second story of a two-story single-family residential building. The deck is wood-framed and includes a wood-framed guardrail system that is framed on the outer face of the rim joist. We will consider the application of design loads at the top of one of the guard posts and determine the forces that are developed at the base connections. We are going to use loading defined in the International Residential Code or IRC. The loading defined in the IRC is similar to the loading defined in the International Building Code or IBC. According to Section 1607.9.1 of the IBC, handrails and guards shall be designed to resist a concentrated load of 200 pounds. In addition to this, the IBC in Section 1607.9.1.1 also requires the guards to be designed to resist a linear load of 50 pounds per linear foot. The 200-pound and the 50 pounds per linear foot loading are not intended to be considered as acting concurrently. The force producing the highest effects governs the design. What does it mean when we say that the force producing the highest effect governs the design? If we apply the 200-pound force at the middle of the guardrail of the deck shown, the load will be distributed to the two posts supporting the guardrail. But if we apply the load directly above one post, that post will need to resist the entire 200 pounds unless we have designed a very stiff guardrail that can distribute the loading to the other posts. While most guardrails can distribute the load to nearby posts, each post is typically designed to resist the 200-pound load. Therefore, we can see that when considering the 200-pound load, the highest design force that each post will see is 200 pounds, which occurs when the loading is acting at the top of the post. For the uniform load is acting at the guardrails. Therefore, we have a 50 pounds per linear foot load acting at the guardrails and pushing outwards. The guardrails are acting as beams in bending and are supported by the guard posts. Therefore, if the spacing of the guard post is 4 feet, the tributary of each post is 4 feet, which means that the total reaction at each post is 50 pounds per linear foot times 4. This is 200 pounds. Therefore, each post will support 200 pounds at the top. This is similar to the concentrated load that we discussed. We can see that if the spacing between the posts is more than 4 feet, the load will be higher than 200 pounds and should be used in the design of the post instead of the concentrated load. On the other hand, if the spacing of the guard posts is less than 4 feet, then the load at each post due to the uniform load will be less than the 200-pound concentrated load. This means that the 200-pound concentrated load should be used in the design. This is what it means when we say that the highest load should govern the design. Before delving further into the specifics of the anchorage requirements for guards, let us step back and consider what the code says about where guards are required to be provided. Additionally, we will look at important considerations with respect to how the framing between the primary guard posts should be designed and installed. For residential construction, the International Residential Code in Section R 321.1.1 specifies that guards shall be provided for those portions of open-sided walking surfaces including floors, stairs, ramps and landings that are located more than 30 inches above grade or floor surface. The 30-inch height is measured from any point on the adjacent grade or floor surface within 36 inches horizontally to the edge of the raised surface. This means that any deck that is raised 30 inches or less above the adjacent grade, considering the lowest point within a 36-inch wide area immediately below the deck, does not require guards according to the code. This does not mean that guards should not be provided. Rather, it means that a jurisdiction enforcing the IRC without any local amendments to this section will not require guards if the 30-inch limit is not exceeded. Another important point worth mentioning is the limitation on openings along the length and height of the guard. Guards may be fully covered with exterior finish or framed with openings, as is the case where vertical pickets are supported between a top and bottom rail. The structural elements that are provided between the primary guard posts and guard rails are also referred to as guard infill components. For cases where there are openings within the guard infill components, Section R321.1.3 of the Code specifies that such openings shall not allow the passage of a sphere that is 4 inches in diameter. Research and experience have shown that a 4-inch diameter is small enough to prevent a child from squeezing through. Therefore, to meet this limit, the spacing between the pickets or any other infill component and the spacing between the bottom rail and the floor should not be more than 4 inches. Lastly, we have noted that in general, guards need to be designed to resist a 200-pound concentrated load or a 50-pound per linear foot uniform load acting at the top rail. We will look at the specific requirements for residential construction shortly. In addition to the loading on guards, the International Residential Code in Section R301.5 requires guard infill components to be able to support lateral loading. According to Table R301.5, guard infill components must be able to support a horizontally applied normal load of 50 pounds on an area equal to 1 square foot. This means that the infill framing members and their connections must have sufficient capacity to support this load. This was a short detour that served to highlight other important requirements related to guards in residential structures. For all other structures that are not covered in the International Residential Code, the requirement for guards are provided in Section 1015 of the International Building Code. Let us now go back to the loading on guard posts. The requirement to check which of either the concentrated load or the uniform load will produce the largest demand load at the guard post is a general requirement that applies to all guard rail systems at elevated exposed edges. However, for a single-family home, the IBC does not require consideration of the uniform loading. This means that we only need to check against the 200-pound concentrated load acting at the top of the guard post. This is consistent with the International Residential Code, which requires checking against the 200-pound concentrated load only. Since this is a residential project, we will focus on the requirements in the International Residential Code as far as the loading is concerned. However, when looking at the design considerations of the anchorage at the base of the guard post, we will need to look at the National Design Specification for Wood Construction, which is referenced by the International Building Code. You may be wondering if the International Residential Code has requirements for construction of guard posts. As far as the structural design of residential buildings is concerned, the International Residential Code provides what are known as conventional construction provisions. These are prescriptive provisions that may be used to design and construct 1 or 2 family homes and townhouses. In most states and jurisdictions, all persons, including individuals that are not trained as engineers or architects, are permitted to use these provisions to design 1 or 2 family homes as well as townhouses. Please check out the complete training series on the design of residential structures according to the International Residential Code at www.conventionalframing.com. The course series is divided into 4 modules, including the roof framing module, the wall framing module, the floor and deck framing module, and the wall bracing module. This is a comprehensive training series that includes a complete design example of a 2-story single-family home using the provisions in the International Residential Code and the development of construction drawings. The course is approved by the International Code Council to provide continuing education units or CEUs. As far as the anchorage of guard posts is concerned, the 2024 International Residential Code lays out the intent in Section R507.10.1 by stating that guard loads shall be transferred to deck framing with a continuous load path to the deck joists. However, the same code does not provide the specific connection requirements between the guard post and deck framing as it does for other deck framing connections. In other words, although the IRC provides framing requirements for the deck joists and beams supporting the guards in Section R502.11, it does not specify the location, size, and number of fasteners required to attach the guard post to the deck framing at the edge of the deck. In this video, we will look at the considerations for the design of this connection according to accepted engineering practice as governed by the IBC. As we noted previously, we will use the loading requirements provided in the IRC. The loads that guards are required to be able to support are provided in Table R301.5 of the International Residential Code. According to this table, guards must be designed to resist a concentrated load of 200 pounds. Footnote I, which is referenced at the requirements for guard rail loading, provides additional information as far as the direction of loading is concerned. According to this footnote, where the top of a guard system is not required to serve as a handrail, the single concentrated load shall be applied at any point along the top in the vertical downward direction and in the horizontal direction away from the walking surface. This means that we need to consider both vertical downward loading and lateral loading acting at the top of the guard post and pushing outwards from the deck. We are not required to check against forces pulling inwards unless the guardrail also functions as a handrail. The guards shown here are not serving as handrails. Therefore, according to footnote I, we are only concerned with the vertical load acting downward and lateral load acting outwards. Please note that the same footnote also states that the concentrated loads shall not be applied concurrently, which means that the designer is permitted to consider these loads separately without subjecting the connections to combined stresses from both the vertical load and lateral load acting at the same time. According to Section 321.1.2 of the International Residential Code, the minimum height of a guard system at open-sided walking surfaces, including balconies, shall not be less than 36 inches. However, there are some jurisdictions where the minimum height of a guard system is 42 inches. According to Section 312.1.2 of the California Residential Code, the minimum height of a guard system is 42 inches. It is important to note that the California Residential Code is adopted from the International Residential Code, where the minimum height is 36 inches. Therefore, the change from 36 inches to 42 inches represents one of the amendments in the process of developing the California Residential Code by adopting the International Residential Code. Please check out our video on U.S. building codes, where we discuss the international codes or I-codes by the International Code Council and how these codes have been adopted throughout the United States. For this example, we will use a guard rail height of 42 inches from the deck walking surface. Let us consider a guard post attached on the side face along the perimeter of a deck. As we have said, the height from the top of the guard post to the deck surface is 42 inches. For this example, we will assume that the decking consists of nominal 2-inch thick lumber, which means that the actual thickness is 1.5 inches. The distance from the top of the deck joists to the center of the top anchor bolt is 2 inches. The distance from the top anchor bolt to the bottom anchor bolt is 5 inches. The distance from the bottom anchor bolt to the base of the deck joists is 2.25 inches. This means that the deck joists are 9.25 inches deep in actual dimensions or 10 inches deep in nominal dimensions. We have said that the distance between the bolts at the guard post anchorage is 5 inches. This distance is selected by the designer based on many factors, including the depth of the deck beam or rim joist, the limiting maximum distance from the bolts to the edge, and the limiting maximum distance between the bolts. The allowed minimum and maximum distance in wood framing members are provided in the National Design Specification for Wood Construction, or NDS, which is referenced by the IBC in Section 2306 for allowable stress design and 2307 for load and resistance factor design. According to Section 12.5.1.3 of the NDS, the spacing perpendicular to grain between the outermost fasteners shall not exceed 5 inches unless special detailing is provided to accommodate cross-grain shrinkage of the wood member. If we consider the guard post, the two bolts are laid out in the direction parallel to grain. However, the bolt spacing at the beam is perpendicular to grain, which means that the limitations in Section 12.5.1.3 will apply. Therefore, we need to limit the bolt spacing to a maximum 5 inches to comply with this requirements. Cross-grain shrinkage refers to the dimensional change that occurs in wood perpendicular to the grain or across the width or thickness of a member as it loses or gains moisture. According to the Wood Handbook in Chapter 4, which covers moisture relation and physical properties of wood, wood is an anisotropic material. This means that it expands and contracts at different rates along different directions. Wood shrinks and swells the most in the direction perpendicular to grain and only slightly in the longitudinal direction. When a wood member is connected using a row of fasteners perpendicular to the grain like bolts or nails along the width of a beam or post, and the wood dries out, the shrinkage across the grain can lock the fasteners in place or introduce unintended stresses. If the spacing between the outermost fasteners is too wide, the wood between them can shrink significantly, while the fasteners remain fixed to the adjoining piece, which may not shrink at the same rate. This mismatch can induce high stresses around the fasteners, which will lead to splitting or crushing around the fastener holes. The 5-inch maximum spacing limit in Section 12.5.1.3 of the NDS is a practical safeguard. By keeping the fasteners closer together, the differential shrinkage across the fastener line is limited, reducing the risk of these problems. If a designer wants to exceed the 5-inch spacing, they must include special detailing to accommodate cross-grain shrinkage. Please note that any solution must comply with all other code requirements and must maintain the overall safety and stability of the structure. Let us now calculate the anchorage forces. The lateral force applied at the top of the guardrail generates an overturning moment at its base anchorage. To maintain equilibrium, the anchorage system must resist this moment by developing an equal and opposite restoring moment. If we take moments about a point at line B where we have the bottom bolt, the loading moment arm is the distance between line A and line B. This distance is 50.5 inches. Therefore, the loading moment is the product of 200 pounds and 50.5 inches, which is 10,100 pound-inches. While the 200-pound force is pushing the guard post outwards, the upper bolt and anchor device are providing resistance against the outward rotation moment. The resisting moment is the product of the force in the upper bolt and the distance between the upper bolt and the point of rotation, which in this case we have specified to be a point along line B at the lower bolt. Since the resisting moment and the loading moment are equal, and since the loading moment and the resisting moment arm distance are known, we can solve for the force at the upper bolt and anchor device. Therefore, the demand force at the anchor is 2,020 pounds, which is 10 times the lateral force at the top. The design engineer would need to provide an anchor with sufficient capacity to resist this force. Similarly, the connection must also be checked against vertical load. In this case, the guard post is supported vertically by the beam at the edge of the deck. The vertical load at the guard post is transferred to the beam through the shear strength of the bolts. Before concluding on the analysis of the deck post, let us briefly highlight a critical assumption that the preceding analysis is based on. When calculating the resisting moment, we took moments about line B in order to calculate the tension at the upper bolt. The choice of line B as a point of rotation is solely based on the fact that this is an identifiable point of attachment between the post and the deck framing. This choice was not necessitated by any principle of mechanics. Choosing line B implies that this is the center of compression if we consider the guard post pressing on the deck framing at the bottom portion of the post while the top portion is pulling away but held in place by the upper bolt. However, if we engage the necessary principles of mechanics in the determination of the actual centroid of compression, we will find that the centroid of compression is lower than line B. Such analysis will be based on certain assumptions, including the rigidity of the guard post. If the centroid of compression occurs below line B, the tensile force at the bolt will decrease. Therefore, using line B in the preceding calculations represents an upper bound and embodies essential conservatism given the role the guards play as far as the safety of deck users is concerned. Please note that the primary objective of this video is not to prescribe or enforce a specific methodology. Rather, It seeks to highlight critical considerations in the design of anchorage systems at guardposts and to provide an appreciation of the magnitude of forces typically involved. Ultimately, the aim is to raise awareness of the structural implications of such installations and to emphasize the importance of engaging qualified design professionals when implementing these systems to ensure safety, compliance, and long-term performance. Another important consideration includes ensuring that the compression stress at the bottom part of the post that is bearing on the deck framing does not exceed the allowable compressive stress. This would not be a critical concern if the center of compression is at line B, as we did in the preceding calculations. This is because there is sufficient wood material below line B to ensure that the average compressive stress is less than the allowable stress. The designer should always ensure that the forces on members bearing on each other do not exceed allowable forces. Another important consideration concerns the bolt installed at the anchor. As the guard post is trying to pull away and the anchor is pulling it back in place, the post will be bearing on the washer placed before the nut. The washer must be adequately sized to ensure that the bearing surface does not fail in what is known as compression perpendicular to grain. A washer with a sufficiently large surface area distributes the force over a larger area, thereby minimizing the compressive stresses. So far, when looking at the anchor connection, we have looked at the transfer of the loading from the guard post to the deck framing. The next item that a designer needs to consider is whether the framing element that is receiving loading from the guard post is adequately supported to prevent rotation or rolling over. Let us look at the case of a guard post supported at the outer face of the framing member at the edge of a deck. Let us assume that the designer or contractor did not provide an anchor device. In this case, if we apply the 200-pound force at the top of the guard post and the edge member will rotate outwards and pull away from the deck. This means that the system will fail and is therefore not adequate. By providing the anchor device, the moment causing rotation at the base is resolved into a tension and compression couple that transmits the force directly into the deck joists that are framing perpendicular to the edge of the deck. The deck joist then puts this force into the decking, which is attached to the deck joist. The International Residential Code specifies the attachment requirements for wood decking to the joists in section R 507.7. So far, we have only considered the deck edge that is perpendicular to the direction of the joists. What about the edge that is parallel to deck framing? In this case, wood blocking with the same depth as the joists is provided to support the anchor. Once the force is transferred into the blocking, the design engineer must design connections between blocking and the decking above to ensure that the force can be transferred to the decking above. The decking will then distribute the force to the other joists. If the analysis reveals that the connections between the blocking and the decking are not sufficient, the designer will typically extend the rod into the second bay. In this case, they can count on the fasteners in the first and second bay blocking as well as the nails in the two joists adjacent to blocking to transfer the loading to the decking for distribution to the other joists. The ultimate solution is the product of analysis and design that shows all elements have sufficient capacity to support the loading. We cannot conclude this video without briefly discussing corrosion protection requirements for connectors and fasteners. In most cases, decks constructed using exposed sawn lumber need to be preservative treated. Some preservative treatments are highly corrosive to steel, especially in wet conditions. Therefore, Table R 507.2.3 of the International Residential Code specifies that connectors and fasteners used in deck construction must be coated for protection against corrosion. For nails, the code requires hot-dipped galvanized nails per ASTM A153 Class D or ASTM A641 Class 3S for fasteners not exceeding 3/8 inch diameter. Stainless steel, silicone, bronze, or copper alternative finishes are also permitted. For bolts and lag screws, the code requires hot-dipped galvanized bolts and lag screws per ASTM A153 or mechanically galvanized steel. Stainless steel, silicone, bronze, or copper alternative finishes are also permitted. For metal connectors, the code requires ASTM A653 type G185 zinc-coated galvanized steel. Other requirements and alternatives are provided on Table R507.2.3 of the International Residential Code. What do you think are other considerations that must be kept in mind when designing and constructing the anchorage connections at the base of guard posts? Please leave your comments in the description. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Please check out the next video on the anchorage of guard posts at the top surface of the deck framing. Thank you for watching.